Thank you very much for the intro. My name is Jakob Foerster. I'm doing a PhD with Shimon, Whiteson and Nando Freitas at Oxford University. I will talk today about learn to communicate. This work is being done at Oxford with my co-author Yanis Asael. We're obviously not the first people to realize that communication is special and that my clicker doesn't work. Okay. I think this clicker doesn't. It's at the top. Sorry, guys. In the beginning was the Word, and the Word was with God. Citing here from the Bible, John et al., Judea 90 AD. It was also realized early on that communication is important to allow a variety of people to collaborate in a setting. As one people speaking the same language, they have begun to do this, then nothing they plan to do will be impossible. Jas et al., Genesis, Judea. Much, much later, the scientific community jumped onto the topic. And even the peace-loving French were so intrigued by the question of communication and the emergence of communication that the French Academy of Science had to ban publications on the topic in 1866. Now, 150 years later, we're asking ourselves the question, what can we do with a communication topic with a state-of-the-art artificial intelligence toolbox? What can deep learning, deep reinforcement learning add to the question of what it means to communicate, what it means to learn to communicate, and how does this lead to intelligence of a human level? Obviously, if we want to study communication in a reinforcement learning setting, the first question is, what's our background? What's the setting we're in? Obviously, we have to have multiple agents, otherwise there's no need to communicate. We're also looking at reinforcement learning settings that are cooperative, where the agents share reward. Imagine we're in one big team and we all get the same points. We have partial observability. If all the agents know everything there is to know, there's no point in communication. And we have discrete communication channels, which means these different agents that are trying to solve a task together, this teamwork, they can exchange specific bits of communication as part of solving the task. And just before they have to solve the task, they get a training phase. We call this the centralized learning phase, where they can all work together and collaborate, exchange information freely. But the strategy they have, that they come up with, has to then be decentralized, where they can only communicate with the specific bits provided in the channel. And most importantly, there's no protocol provided. So we have a team, imagine you're the team, you have a channel, and you can exchange bits in this channel, and you have to solve a task. And each one of you knows something that the other side doesn't know, but you're not being told how to use this channel. So you have to come up with a way of exchanging communication, of exchanging information through this channel as part of solving the task. And I was told there could be questions coming up here. Seem to be lucky or unlucky. Nothing so far. Given sort of like the mixed background of people in the room, I'll start with a brief intro. By the way, are there any questions about the setup so far? No? Yes? So yes, so in this setup, we're looking at cooperative settings where the rewards that the agent receive is the same for all of the agents. So we're a big team. Okay. Now, just brief background on reinforcement learning and then on DQN, which is the underlying toolbox that we're using in all of this work. Reinforcement learning in general concerns itself with an agent and an environment. The environment is symbolized by the Atari box, the agent is the brain. The agent, given a state, an observation from the environment, needs to take actions. The actions lead the environment to carry out a state update and send rewards to the agent. And the goal of the agent is to maximize the total reward that it receives over an episode. So it's a very generic framework, which is why a lot of people are excited about this and believe that this can help lead a way to very smart algorithms and machines. One of the most robust reinforcement learning algorithms that has been very popular in the last 10, 15 years is called Q-learning. In Q-learning, what we do is we learn a Q function, and the Q function tells me, given that I am in a certain state, I'm making a certain observation, what's my total reward expected for each of my actions? The actions here being symbolized by the controller on the slide. And obviously, once you have this Q function, then life is really easy. Because in any state, you can just ask yourself, what are the best actions to take that will lead to the greatest reward in my current state. However, if you imagine you have a big table that has all the possible states and all the possible actions in it, then for something like an Atari game that has exponentially number of states and number of pixels, that's infeasible. So this toolbox became much more powerful when it's combined with deep neural networks. That's called DQN. In DQN, we use a deep neural network shown on the right-hand side that maps from the pixels of the screen, from the actual Atari screen, the computer game, to the expected reward for my different actions. And this was popularized in 2013-14 by the guys at DeepMind. And that's really the fundamental underlying toolbox. We're learning a Q function. The Q function is parameterized by weights, and we can adjust our weights to improve the loss function, which is on the bottom, which captures the difference between my expected reward and the actual reward for the episode. So the agent goes through a learning algorithm where they pick actions based on the Q values. I'm asking what's the best action to take right now. And then I look at the actual reward and I update the weights of my network to reduce the DQN error. That's the loss function. A difference between action and estimated reward given the stated action pair. However, we're not done with the background because, as I said before, we're partially observable. And this has been done before. People have combined DQN with partially observable setups. In those settings, only part of the current state is visible. You don't see everything that's relevant. This work was done by Matt Hausknecht, and he deleted a fraction of the screens of Atari, which meant that now the agent has to remember, oh, I can't see anything right now, but I remember the previous screens. And how do you remember with neural networks? Recurrent neural networks. So they used LSTMs in combination with the Atari DQN network, and then you see an unrolled DQN network across 2 time steps. Right? So there's an LSTM at the top layer here. That's a recurrent neural network architecture. We're receiving at each time step the processed image through our convolutional networks. We're then producing both the Q values and a new memory vector that goes into the network at the next time step. And that allows us to have memory and statefulness for the agent. The agent's behavior can now condition on the entire observation history rather than just the current screen. And that's very powerful for partially observable systems. The second thing we need is we need to address the question of multiple agents. How do we do reinforcement learning when there is 200 people in the room? Well, simple answer is each one of them becomes one network. That's been done, that's called distributed Q learning, where we have one DQN network for each of the agents present. And then in the environment, if you think about it like at a high level, you now have 2 action spaces where each of the agents takes the action. The environment receives the actions from all of the agents and then produces new states and rewards for all of the agents. And we can now train those 2 networks, and this was done using Pong. So you have multiplayer Pong, 2 people playing together. And each of these agents is represented as a network. Questions? I see a lot of confused. Yeah. So we haven't gotten to communication yet. So far we've covered partially observable systems. I can't see everything that's happening that's relevant. I have to remember. And we've covered multiple agents. I'm not by myself anymore. And that was a wonderful gateway because now we're getting to multi-agent RL with communication. So we're combining all of the ideas from above. My agents are now recurrent neural networks, and we have multiple of them, and now we have a communication channel. So the blue thing here indicates our discrete communication channel through which agents can send messages back and forth between each other. Note that the messages don't interact with the environment with the simulator. That's a separate, that's a separate part of the screen. The messages don't change the reward, they don't change the state update, they don't change the outcome, what happens in the Atari box. Think of 2 people playing Atari, and they're talking to each other while they're doing so. Right? It doesn't go into the environment. And now the question is, how can we tackle this setup? What's the best way of allowing these agents to communicate in order to solve tasks in this setup way? Questions? No questions. So either I'm a very good communicator or very bad. Nothing in between. Moving on, we are proposing and comparing 2 different methods here. The first method we call differentiable interagent learning, or DIAL, and the second method, reinforced interagent learning. The interagent learning is just to make a nice acronym. The important parts are differentiable and reinforced. Keep those in mind, RILE and DIAL. They'll come up over and over again. RILE, reinforced interagent learning. At the core, treats the act of sending a message to an agent like another action. And what this means is, how do I choose my actions? Well, I have Q values for them. My deep Q network, that is recurrent because it's partially observable, and many of them because it's multi-agent, my deep Q network now produces Q values not only for the actions, which way to move, what to do, but also for the messages. What message do I send? And we did a few modifications here to the baseline, where we include the last action input because it's partially observable, and we do parameter sharing between the agents because it's a deep neural network, we can do this. And this allows that all of the agents can sort of like aggregate the experience in the learning and learn much, much faster. But at the heart, as I said, what to communicate is based on the action, based on the Q value, right? So the Q network here, so if you look at the diagram, you see two agents broken out, one in each row, two time steps, because we have to unroll over time. There's the Q network that receives the observation of the messages. It then produces Q values, and we select which action and which message to send with an action selector. That's typically epsilon greedy, if this means 70 people. And then, importantly, the message goes off to the next agent, goes off to the top right, the MT1, and the action goes to environment. The environment then produces new rewards, and I can calculate a DQN error. What's the error? How accurate was my prediction, and what reward did I actually receive? The gradient, the red line, doesn't cross between the agents. It goes from the environment to the agent, but there's no gradients exchanged between the agents. So essentially, if you imagine all of you are individual RILE agents here, you would all be doing your own little thing. You would receive inputs from the others in terms of messages. But to calculate your gradient updates, how do I change the parameters in my network to reduce the error? You would not have to receive any input from the other agents. But we are taking advantage of parameter sharing already here because we are deep networks, we can actually do this. And this does speed up the learning. In DIAL, in differentiable interagent learning, we're using the fact that these networks are end-to-end differentiable. And what this means is, and this is a little bit like the little nods that I get when somebody understands what I'm saying, that there can be a feedback mechanism. The sender can receive an update from the recipient about how to modify their message to make the world a bit more clearer. And making the world clearer means reducing the DQN error. So here we're sending back a partial derivative of the recipient's DQN loss with respect to the incoming message. And that's symbolized by these red lines. The red lines now cross from the recipient of the message to the sender. And we can only do this because all of the agents are deep Q networks, which means that the grade is actually well defined. We can differentiate through the entire agent end to end. So what this means is, specifically, I receive a message here from the front row. I then take this message as an input. I look at all my other inputs. I look at my Q values. I pick an action. The action goes to the environment. I receive an error back, a Q error. This was an inaccuracy. And then I can calculate, because I'm differentiable, I can calculate the derivative of my DQN error with respect to the incoming message. And I can send this back to the sender and say, why don't you update your message in this direction? And the sender can then change their weights to modify the message so that it reduces my DQN error. And now we can exchange gradients. We're both using both the parameter sharing and the gradients during the centralized training phase. Obviously, none of this works, obviously, because it's a discrete channel. How do you differentiate through a bit? Well, the answer is you can't easily. So during training, we actually represent these messages, which are binary vectors, as continuous variables. And in doing so, then, you can ask yourself, well, what happens at execution time, where you're only allowed to send these single bits, and you've learned a continuous variable, and I write down like 0.1576. No, you can only send 0.1. You have to binarize, right? So this is the little DRU unit here. So the message from the CNET goes to that little unit that discretizes and regularizes. And essentially, during the execution phase, it just discretizes into 0 and 1. And during training, we want to encourage the network to learn values that can be discretized well. And that's done by adding noise. So we have the sigmoid function with a noise. So you can see for an incoming message, that's the distribution of outgoing messages here on the right-hand side. And this noise really affects messages in the middle of the range, and it gets sort of like squashed by the sigmoid at the tiles of the range. And this encourages the agents to learn protocols in this continuous channel that can then be discretized. Any questions? Cool. Yes? It's broadcast. The question is, how many messages can an agent receive? And the answer is, it's sort of up to you to design the task. In the task we're looking at, um, there's typically only one of the agents that can broadcast to the others, and the others receive. But it is really up to the design of the task. This algorithm itself is generic. You just have to be careful with your gradients to make sure that the sender and recipients exchange gradients appropriately. Oh, fantastic gateway. So here's, so if we're doing parameter sharing, where all the agents have their individual, the same parameters, then there's something that they receive here as an input at the bottom. So we have the observation, we have the message from the other agent, we have the last action I took, and we have an agent identifier, a number. And this basically gives you 128 weights that you have as a sort of like, you know who you are because you can learn a sub-policy within the shared. There's a lot of shared weights, but there's some weights that are unique to the agent that identify them. So if you want to learn specialization for the agents, you can with a setup. Yes?
You mentioned before that those agents are communicating without any protocol, but uh, there is there is an agent number, there is an agent ID. They are sharing messages, or they know how to share messages. That mainly means that there is a protocol.
So I think there's a meta protocol. There's a protocol on how to find protocols.
Okay.
Because the
Fair
meaning of
enough.
the messages themselves is not identified.
Yeah.
How to learn the messages, that is identified.
Yeah.
Very good question, by the way. Sorry, actually I should talk about the slide. So what we're showing here is the architecture, and we're unrolling because the GIU, it's a recurrent neural network, we're unrolling over time. So we're showing how the information flows through the network. We have the input network that processes the input. It then goes to the GIU, which produces a hidden state going off to the right, which is consumed at the next time point. It's the memory vector. And at the top layer of the GIU, in the second green row, we're then producing something that gets to the output network, which produces the messages, which are continuous values, and the Q values. They call this a CNET for communication. But that's basically what it does now. We're producing two different types of outputs at the top of the network, one of them being the Q values for the actions, and the other one being the continuous variables that we send in the channel, which could then get sent to the DIU, and. So those are the messages. And that's the architecture in general. It's a relatively generic architecture you can use for different tasks. And we can obviously play with this question of centralized learning, parameter sharing or no parameter sharing, as we see it fit. Here's the first task. So if you think this talk made sense so far, this is where it's becoming more interesting. It's a riddle. It's a very famous riddle. I encourage you to just read through it. I'll do it myself as well. Quick show of hands. Who has seen this riddle before? Good. Do you know the answer? Those of you who don't know the answer from before, can you think of one quickly? It's actually pretty hard, so I'll be very impressed. But long story short, this riddle is something that existed before I started working on communication, and it's typically thought about as being something that you present to a central planner, like somebody in an interview, or another agent that should make up their mind about how to communicate between these different prisoners. However, we can reconsider this as a problem whereby each of the prisoners now is an AI agent, and the light bulb that they can use to exchange information is actually a communication channel. Because remember, in the problem setup, you have these 100 prisoners, and each of them goes to this room where they have a light bulb that they can turn on or off, and the next day another random prisoner sees the light bulb, and they can tell the prison ward if they think everyone has been to this room. So if all of you have been to a specific interrogation room, then we can terminate the episode and be all set free. If it's false, we all die. Now this is an RL problem. We get +1 points if we all set free. We get -1 points if we all die, and 0 points if the episode expires. And we have a communication channel of one single bit that gets sent from the prisoner in the interrogation room today to the prisoner coming in tomorrow. Does that make sense? And we've now rephrased this problem, which has been around as a central planning problem for interview questions and brain teasers, as a multi-agent reinforcement learning problem with communication. And we can now unleash our tools that we described in the last 10 slides on this problem and see what happens. And obviously, this all sounds really like nice and cute. You have a little switch that you can play with. Sounds pretty simple. However, it's actually a really, really hard problem. Because it's partially observable, your action space, your policy conditions on the entire observation history. So the number of policies you have to consider if you did a brute force search grows as 4 to the n number of agents, 3 to the t length of the episode, which means double exponential in the length of the episode. And even for a modest number of 4 different prisoners, there's already 4 to the 350,000 different policies that you could consider. So if you can make progress on this, that's fantastic, because obviously brute force search will not get us there. Now, getting to the results. What we're showing here is the results for DIAL and RILE for differentiable interagent learning and reinforced interagent learning with and without parameter sharing on 3 and 4 agents. And we're also showing a non-communication baseline. We want to make sure is that these agents are actually learning to communicate. So we're comparing the performance on the task and the setup where we break the channel and they cannot send information. Because are they actually using this channel efficiently? And as you can see, DIAL, the green line, with parameter sharing learns immediately for 3 agents. And to some extent, everything still works for RILE without parameter sharing. Everything exceeds the baseline and it works. However, for 4 minions, if you don't use parameter sharing and you use reinforced interagent learning, which is the entirely decentralized learning case, you don't learn to communicate, which is shown by the dashed blue line here, not exceeding the yellow line. And the other cases really get very close to the oracle. So what we're showing on this slide is that really if you do use the fact that you're centralized and you use deep learning to exploit the central training phase, then you can really learn these communication protocols that are somewhat non-trivial. What's also very interesting is that because we are in a discrete channel, we can analyze these protocols and ask what strategy did it correspond to. Now, before I go there, can anyone tell me how to solve the problem for 3 prisoners? 3 prisoners, interrogation room, they have to figure out who has everyone been to this room, and they're randomly chosen with replacement, and the only way to communicate is through the light bulb. How do you solve this problem for 3 prisoners? Which obviously the AI agents here have solved within whatever this is, 100 episodes. Does anyone have a suggestion for how to solve it? Well, in that case, congratulations, the AI wins against. Well, here's the answer. That's how they solve it, right? If you look at the protocol, if you look at what the messages they're sending to solve this task, there's really only 2 different options you have to worry about. If 3 prisoners had been, the episode would be terminated. So if I come in on day 2, there's only 2 possible states of the world. Either 1 person has been or 2 people have been before. Because the 3rd person would have terminated the game. So if I'm still there, that means the game hasn't been terminated. So what these prisoners do is they use the binary position of the switch to encode the 2 options. When the light is on, it means 2 people have been. When the light is off, it means 1 person has been. So you follow the branch here. If I come in and I haven't been before, on like day 3 or plus, if I have been before, I do nothing. Because the state of the world hasn't changed. I have been before, not more people have been. Because whenever 3 people have gone to the room, there's only 3 prisoners, we have to terminate because everyone has been to this room. Okay? I do nothing. If I haven't been before, then the state of the world has changed. The count needs to be incremented. But does it need to be incremented, or is the episode over? Well, that depends how many people have been before. If I'm number 3, so if the switch is on, and I haven't been before, then that means 2 people have been before me. I haven't been. I must be number 3. Therefore, let's terminate the game. Terminates. Other option, the light is off. I haven't been before. Dip, 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 dip. 1 person had been. I haven't been. Therefore, it's 2. 2 is encodable, light is on. Okay? So this is actually what they learned, these agents. And I hadn't solved this myself before. So I was very impressed because they figured it out before me. Then I posed the same question at the dinner in Oxford, and the law student opposite me solved it in 30 seconds. So I was a little bit less happy after that. But yeah, that's the strategy. And because it's a discrete channel, we can really analyze it. We can take this apart. We can ask, what are these things doing inside? And we can learn something from them. In my case, it was the humble insight of how to encode, how to get out of prison if faced with this warden. Is there a question? How do the prisoners synchronize on equals 1 have been? That's basically the protocol has a lot of redundancies. There's a lot of different ways to encode this. And you could also flip it around. You can make it 1 equals, 1 equals on equals off. I mean, this is basically just showing an interpretation of the protocol that's the same messages, right? Because remember, the protocol wasn't done as a switch. It's just a binary bit. And we're just, for representation purposes here, mapping this into on and off, right? But in principle, you can agree on either 0 or 1 to be whatever you want, because again, no protocol is provided, right? We have a meta protocol for learning protocols, but no actual protocol. I hope this clarifies. Cool. So because we are using deep neural networks, there's more we can do. Yes, we can be recurrent and we can do all this differentiation, but what are these things good for? Rich image spaces. So looking at visual input of 28 by 28 MNIST digits is now possible. So the next task concerns itself with 2 agents that are each receiving 100 digit. In the first task, so you see the input to agent 1 at the bottom, so I'm not talking about the left-hand side here, and the input to agent 2 at the top. They receive handwritten digits, MNIST, in red and green, and they can only send a single bit across to the other agent, after which they have to take an action. The problem is the action depends both on the parity of the other agent's digit and on the color. Now you can send a single bit, what do you do? Well, that's the hard part. It turns out that parity is harder to learn, but gets greater rewards. So we have a setup here where there's insufficient information to take the right action, and you have to agree on the protocol to use here, because you can either use parity, encode parity, or encode color. And the second setup, each agent receives 100 digits in black and white this time, good old style MNIST, and they can send 1-bit messages across 4 time steps. So each time step, they're sending a bit, they're receiving a bit, make a time step, receive another bit, and so on. After they've received 4 bits, they then have to guess what digit the other agent is looking at. And they get 1 + 1 reward if they get it right, they get 0 reward if they get it wrong. And here's the results. So for the first task, we have these 2 competing protocols. Both methods, RILE and DIAL, do learn something, which is nice. But again, using gradients is much, much more powerful. You can see the green line at the top. Obviously, if you don't communicate, there's a baseline here. You don't get any rewards. And sharing parameters helps a lot. For the second case, where it was about guessing the digit, so I have my digit, you don't see it. I send you 4 different bits one at each time step. I now, again, see a strong outperformance of DIAL, but actually with reinforcement learning, you don't learn any protocol. You don't exceed the non-communication baseline. And that's kind of intuitive, because mapping from 28 by 28 digits, pixels, into these 4 separate messages, and coincidentally finding an encoding by random search, which reinforcement learning is at the beginning, is highly unlikely. Any questions on this? Again, because it's discrete, we can ask ourselves, how did these agents actually send over the message? Now, well, you have 100 digits between 0 and 9, and you have 4 bits. Easy, right? You build a decision tree. And that's basically what these agents ended up doing. Right? So here we're showing at each step, given that they're looking at a certain true digit as an image, which we didn't tell them is a digit, we just tell them is an image, that's what they end up sending. They send, if they are at step 3 and they see a 0, they send a 0. If they were looking at a 8 instead, no, at a 7, they would send a 1, right? But if you aggregate these 4 bits that they receive at each time step, you have a unique identifier for each of the possible digits. So they've learned a binary code. They've managed to map from a 28 by 28 real valued pixel to a binary code. That's the task. That's how they solve it. That's the protocol they learn. And I mentioned before, to do all of this, we have to have continuous messages, so we can actually pass the gradients backwards during the training process in the channel, and we need to be able to discretize them afterwards. Therefore, we added noise. But does it actually work? Yes, it does. So if you don't add noise on the left-hand side, sigma equals 0, in the channel, the activations remain tightly clustered around 0. Obviously, if you have sort of like one big blob and you cut it in the middle and say this is 0 and this is 1, you're going to make a huge discretization error. However, if we add noise on the right-hand side, sigma equals 2, that's the Gaussian noise in the channel, then these messages over the course of training split into two separate activations, shown here as the like large spike and the small spike. And now you can think about it, if you compare your discretization error, that's the difference between the step function and the tan h. That's exponentially small at -10 and +10. Right? So at this point, when the agents have learned this protocol that really uses only the tails of distribution, we can discretize without incurring a discretization penalty. And we can go back from our centralized training phase or decentralized execution phase using the discrete representations of the messages. And without noise, this doesn't work. So this is sort of like a nice little side note. People have wondered, how does the communication turn discrete? Right? Why are we talking in words and not in sort of like continuous tones? And one of the answers might be we have a noisy channel. And in a noisy channel, robustness of encoding is going to be easier to achieve if you have these sort of like discrete activations. Now, obviously, this is all very exciting, but there's a lot of work to do. Right? We think it would be fantastic to apply this in a setup where multiple agents are actually interacting in a very rich visual environment. For example, a team of Command and Conquer, where people can actually send messages and coordinate and explore together and discuss while they're playing the game. We also think that there's some benefit in dropping this cooperative setup where rewards are aligned, because humans talk in a variety of setups, and not all of them are fully cooperative. Right? We have two football teams that shout at each other. What does that mean? So, for example, I think in poker we could explore the importance of lying and of cheating and of betrayal in communication amongst different agents. And then another option is to ground this, go back to the physical reality, ground our communication, the objects in the real world. And last not least, there's clearly value in humanity in having these universities and having schools. So teaching as a form of communication has obviously helped humans to become intelligent, become what we are. I think everyone here has gone to school, and so have I. And it would be nice to transfer the same kind of thing to AI agents, but it's a very hard task. To conclude, what we've shown is that really using the state-of-the-art deep multi-agent reinforcement learning methods, we can provide a setup where agents can learn to communicate. They can learn these simple protocols to solve tasks, and sometimes these protocols aren't even that simple. And we can do so by exploiting the fact that we have these deep neural networks. We can use the gradients through in-dial and differential interagent learning, and we can use parameter sharing, which lets us aggregate experience across all of us. Imagine if instead of having to come to a conference and having to discuss, you could just merge your minds. Right? That's essentially what this parameter sharing is, because we can just bring all the experience together. Adding noise to the channel helps us to learn messages that can be discretized, although they will learn continuously during training. And because we have discrete messages, we can later on take a step back and ask, what are these agents actually doing? Maybe we want to learn something about the real world, want to learn something about the task, want to understand how they manage to execute this. And last but not least, again, a lot of exciting work to be done here. This is very much the onset of something that we believe can keep going and can become something that a lot of people care about. And to get as many people excited as we can, we've published the code online. So if you have anyone who wants to get started working on this topic, all the code is published. It can be run very easily on any machine. And you can also just send me an email. With that, I would like to thank you for your attention and open the floor to questions.
Right, so thank you for a very, very interesting talk. Shall we take questions? Questions? Do we have?
How robust is this technique against the agents dropping off and appearing over time? Or can that be modeled by noise in the channel?
I can repeat. So the question was, how robust is this technique against agents dropping off and appearing? And in the current setup, we've trained with a static number of agents. But if you train it during the process with agents disappearing and appearing, then it will obviously learn to generalize in that way. Right? So you have to include it against, like in your meta protocol. As it currently is trained, it wouldn't work if you just delete one of the agents. you would have to include that in the training phase, where you bring in agents and drop out agents dynamically. And there has been a line of work similar to this at Facebook AI Research, and they do an averaging of the messages so that it can actually deal better with the dropping off and appearing of agents. More questions? Yes.
Yeah, my question was something tied with the previous question, but I was just interested, like, of course, when you're putting number of agents, how does the complexity varies in terms of time, and also what's the optimal number of agents? Yeah, again, it will depend on the task, but yeah. Have you any experience with that?
So there's two complexities involved, right? One is the complexity of the policy space. If you just make a brute force search, how many policies are there given the number of agents given the task? And there's another complexity. What's the learning complexity? How hard is it to learn this, right? So in our setup, each of the agents is a deep neural network. So there's sort of like your scaling in compute time scales linearly in the number of agents. Because you have to unroll each of these networks. These are all independent DQN networks. And they have to be unrolled, and you have to do the gradients, and. So you get sort of like a linear scaling in the number of agents that are involved in the task. And the optimal number of agents, I mean, obviously the task with the switch gets easier for a small, if you only have a single agent, if I'm the only prisoner and I go to the interrogation room, I'm over. It's because everyone has been, right? And if you have 2 prisoners, it's still trivial, and 3 is like the first task that becomes non-trivial. More questions?
No more questions?
Maybe one
Yeah,
here.
Henrik?
Yeah. Okay, I try to speak up.
Yep.
So what if all the agents do not have to learn the protocol from scratch, but maybe some novice agents enter and adapt to an existing protocol?
I think, so the question is, what happens if not all the agents have to learn from scratch, but some novice agents adapt to an existing protocol? That's a fantastic research question. It goes towards the teaching aspect here, right? How can you adapt a protocol? How can you learn a pre-existing language? I think that's would be fantastic follow-up work.
Okay, thank you. And with that, I think we thank the speaker again. Thank you, Jakob.